In this video, we are going to look at the one-way analysis of covariance, or one-way ANCOVA, which is a test that you should use when you are analyzing a relationship between an independent categorical variable versus a numeric outcome, but at the same time, you're controlling for the effect of a third variable that is numeric. Here is an example of such a data set, which you can get through a link in the description of this video. We have got a total of 60 participants receiving 3 different groups of hypertension drugs. We have drug A, we have drug B, and also a group receiving drug C. Their measurements for systolic blood pressure were taken at baseline before the start of the treatment, and then after the treatment, their systolic blood pressure measurements were also taken, and this is called SBP post. We want to assess the effect of the different treatments on systolic blood pressure measurements while controlling for the effect of systolic blood pressure measurements at baseline, because we think this may also affect the final systolic blood pressure measurement. And to do this, a one-way ANCOVA will be the most appropriate. To run a one-way analysis of covariance, simply go to Statistics, go to Linear Models and Related, then select ANOVA, MANOVA, then choose Analysis of Variance and Covariance. We are going to specify our outcome variable, which is blood pressure measurements after the treatment. Then we are going to choose the 3 dots to set up our model. One of our variables is a factor variable, the categorical variable, and it is a main effect. We are going to specify, that is treatment, the different treatments A, B, and C, and then we add to the variable list. Another variable is the continuous variable, or the covariate, which is systolic blood pressure measurements at baseline, and this is a continuous variable, so we are going to check this box for continuous, and we add this to the list. Then we click OK, and then click OK. So in this output, we can see that the number of observations are 60, R squared, showing us 0.9682, which implies that 96.8% of the variations that we've seen in the outcome can be explained by the model we have fit. We have the adjusted R squared value here. We also have in the table the sources of variation. We have for the overall model, we have for the variable treatment, the categorical variable, and then the covariate, the numeric variable. Here, the partial sum of squares, degrees of freedom, mean squares, and the F statistic. Then we see the overall p-value. For the model, we can see that overall, it is less than 0.05. It is statistically significant. The statistically significant overall p-value for the model implies that by adding these variables into our model, we have significantly improved it. We see that for treatment, the p-value is also less than 0.05, implying that there are statistically significant differences in the mean systolic blood pressure measurements after the treatment for the different drugs used. So at this point, we shall need to do post hoc tests to show us which treatment groups particularly were having higher or lower mean values compared to the other drugs. But before we do that, let us also look at the covariate here. We see that the covariate is also statistically significant, which tells us that the measurements at baseline for systolic blood pressure is a stronger predictor for the post-treatment systolic blood pressure measurements, meaning that higher systolic blood pressure measurements at baseline are strongly associated with higher systolic blood pressure measurements after treatment, regardless of the drug. So you can go ahead and find out for treatment, since there are 3 groups and they are telling us that there are significant differences, we can do post hoc tests to show us the pairwise comparisons for these drugs. So we can go to statistics, go to post estimation here. In this dialog box, we are choosing tests, contrasts, and comparisons. Then we go for pairwise comparisons. Under pairwise comparisons, we choose our variable. It is only 1 because it is the only categorical one we can run post hoc tests for the previous model we've just run. So we select treatment. Under reporting, we would want to check this box for specify additional tables and show effects table with confidence intervals and p-values. Then you click OK. So as the overall is telling us that there are statistically significant differences, here are where the differences are lying. When we check drug B versus A, we see that it is not statistically significant. Drug A and B were similar in their effect on systolic blood pressure measurements. But when we check drug C and A, the mean difference was 11, and this was statistically significant. Similarly, drug C and B, the difference was 12, and so it was statistically significant. So that's how you can run a one-way analysis of covariance. Here is how we can present the results of this analysis. Feel free to customize it to the requirements of your institution. If you found this video useful, consider liking, subscribing, and commenting so that you don't miss out any of our next episodes. Next, we shall look at one-way maneuver, where you have, instead of one outcome variable, you have got several outcome numeric variables that you want to analyze versus a single categorical independent variable. See you in the next episode.